All right. So let's start with today's class. Today's class is going to be shorter than usual because we've laid the groundwork for what we're going to do, and it's going to be pretty straightforward to do things now. So today we're going to define the Feynman path integral and therefore perturbation theory for a scalar field. So perturbation theory in the path integral formalism. We already saw how to do it in operator formalism, but we'll see that the path integral formalism looks a bit different and simpler in some respects. So last time we considered quantum mechanics in the path integral formalism, and specifically we've seen how to treat it in the Euclidean formulation. So we saw that there were several problems with the formulation in Minkowski space. One of them was that if I want to write a path integral in Minkowski space, I have an oscillating phase e to the is, where s is real usually. I mean, that's for a well-defined system, the action is real. And so we have a highly oscillating phase, and since our main tool to perturbation theory is to approximate this exponent with its extremum given by the classical action, that is not necessarily a good approximation if this is a highly oscillating phase. So in principle we want to use the formula for Gaussian integration, but it's strictly speaking not valid for an oscillating phase. And so we saw that one way to deal with this would be to turn the integral into some integral that is of Gaussian type, integral of some e minus s, where in fact you've equated I times the Minkowski action with minus times the Euclidean action. And then this has a classical, on the classical value it has an extremum, and then we can actually use Gaussian integration via the saddle point approximation of this integral. And so we saw that in order to do this, we had to perform what we call the Wick rotation, where Minkowskian time, the usual time, is written as minus I times Euclidean time. And we saw that if we do this to a transition amplitude for quantum mechanics, we obtain that if, moreover, we look for trajectories that are periodic in this Euclidean time length, so q of t plus beta is equal to q of te, and then we integrate also over this boundary condition as for any other field, then we obtain a path integral with periodic boundary conditions. And for this path integral, we obtain actually, so this would be integral dq minus s for q of t plus beta equal to q of t. then this is trace E minus beta H. So this is the actual partition function of statistical mechanics. Hence, we extend this name to also to path integrals, and we call this path integral also as a partition function. And this Feynman-Katz formula is not just a curiosity relating to statistical mechanics, but more importantly, I told you that then the limit when beta goes to infinity, basically in this trace selects just the vacuum energy. So when taking this beta going to infinity limit, and therefore considering zero temperature, the case that's most relevant for quantum field theory, this implicitly, so for this Euclidean formulation, this implicitly gives the so-called vacuum functional, which is what we were actually after. We were after the vacuum functional because we want perturbation theory where the system at infinity is defined to be the vacuum. Therefore, by imposing this periodic boundary conditions, and then in the end considering a very large period, not only have we defined better this path integral, because in so doing, that means that there are no boundary terms, but we find that we obtain the vacuum integral, the vacuum function, which is the thing that we were after, the thing that has physical significance. And finally, the last observation that we made, so one observation was that now Gaussian integration is well defined. The second, that there are no boundary terms, and related to this, that we're actually doing what we want, the vacuum functional. But the last one was also that now there are no more poles in Euclidean space. So the poles are reobtained by the Wick rotation. But if we do a Wick rotation with only pi/2 minus epsilon, then we reach the Feynman propagator. And it's important to stress that, as I showed you last time, the Feynman propagator is obtained through a continuous deformation of the integration contour, but there is no continuous deformation that obtains some other propagator. So the Feynman propagator is unique, it's uniquely defined. All right. What else was there to say? Yeah, so no boundary terms here meant that for the harmonic oscillator, we had obtained just the quadratic piece, the partition function. Z of j was exponent 1/2 j dot delta dot j in Euclidean space. In Minkowski space, in principle, we had also a linear term coming from boundary conditions, but that is not present anymore. All right, so now let's try to generalize all this picture to scalar fields. So from Q of t x mu. Right? I mean, as before, the idea is to think of this somehow as a set of points defined by the positions in space, and then time is the same time. And as we saw at the beginning of the course, this comes with its own issues. We have to be careful, but there's issues of regularization and so on, but I will not bother with that now. The only point is I want to make now is to find a simple generalization based on this replacement. So, and the point is, of course, that we already did this substitution in the case of the Minkowski scalar field. So for the Minkowski action of the scalar field, we found that we had this action, and perhaps isolating the mass term from the potential. And then with this action we found that the relevant objects that we want to calculate, the Green's functions or endpoint functions, were time-ordered products of time-ordered waves of 5 x's. And in the path integral formalism, these were written as path integrals with this d phi e to the I s, and then the insertion of these guys. Okay, so then we want to write the equivalent Euclidean action. And as we said, the weak rotation corresponded to time Minkowski being written as minus I Euclidean time. And I will write this as the standard notation is Tm is x with an 0 up, index 0 up, and remember that to lower and raise the index 0 I multiply with the metric, which is minus 1 in this case, so this is minus x0 down. But then if I am in the case of T Euclidean, this is written as an x4, but of course the Euclidean metric means the index 4 is the same up or down, doesn't matter. So reversely, I would say that also x4, the Euclidean one, is I times x0, the Minkowski one. Okay, and we've seen last time how this goes. Only the integral over so all right, let's do it more carefully. Perhaps let's do it again. So I want I as Minkowski to be equal to minus S Euclidean, right? And specifically, then let's concentrate on these terms without derivative. This involves derivative with respect to time, so let's take it a second. But if I look at this minus d, so I would have minus integral d4, let's call it d3x dx0, minus I. This should be equal to minus d3x dx4. And now I would write the part of the Euclidean action, which is this minus. Okay, and then x0, that is t Minkowski, is minus I times t Euclidean, which is x4. But minus I times minus I is equal to minus. And so in the Euclidean action I have the integral of v of phi. And then similarly for the part from the kinetic term which involves the index I, which has a Euclidean metric. So the term with the minus sign in front here, and then vi phi squared also gives the same kind of term as in here. And then the term with so minus a half then times minus 1/2 d0 phi squared, that is dx0 phi squared, right? In this case, x0, as before, is equal to minus ix4, and minus I squared gives minus 1. So minus I squared removes this. And so on the other side, we'll obtain d4 phi squared. So the same way as for the other terms, which means that all the terms in the Euclidean action are now positive definite. So d4x 1/2 d mu phi plus d of phi. And I wrote the indices down just to remember that this is Euclidean, and up and down in Euclidean space doesn't matter. Right? All right. So this is an important point. This is positive definite. Okay. Now similarly, we do the same transformation on the Green's functions. And so e to the is becomes e to minus se, and the other path integral and phi's remain the same. So we obtain that the Euclidean Green's function is just path integral with e minus s of phi, but then the same thing. And then in the presence of let's say, so for both J source and beta, one of the temperature finite, in the most general case where we have a connection with statistical mechanics, this z of beta and j, which would mean trace E minus beta h with a source j, then this would be a path integral with E minus Euclidean action, but then I would also have the source term j phi, and moreover, since I want finite beta, in this general case I would have periodicity with period beta, so phi of x and Euclidean time plus beta is equal to phi of x and Euclidean time. And in principle, we could derive, therefore, finite temperature quantum field theory from something like this. But as I said, what we're interested in is actually zero temperature and the vacuum functional. So, taking beta to infinity to obtain this vacuum functional, which is then just this path integral with implicit periodicity but infinite periodic, infinite period beta. So therefore the implicit periodicity just means that we don't have any boundary terms, right? But otherwise it has no effect. And I will denote this remembering what really was this path integral came from the product of two Heisenberg states. In this case, when beta goes to infinity, this amounts to the vacuum state. And moreover, we have a source J, so this is really the product of two vacuum states, as Heisenberg states, but in the presence of the source J. Of course, for physical calculation, we would want that the source J has finite domain. I mean, that's really what we want to explore, where we have a vacuum outside some finite region, and then inside it we have stuff happening, including sources. But a priori, since if we think of this not as physical sources, but as some mathematical trick, it could be anything, so I could put a source that is, say, constant. Yeah, and j by phi means just the integral of j and phi. And as usual, the endpoint function, is obtained from the derivatives of the partition function. In fact, the partition function was defined as a generating functional of all these endpoint functions. So that means that Gn x1 xn is now Dn dj x1 dj xn of j at j equal to 0. That is to say, dn dj x1 dj xn, and z of j is this path integral d phi d minus s d plus j phi. And indeed, we see that when we take the functional derivative with respect to j of x, we kill this j dot and we're left with phi of x downstairs. So by taking n of these derivatives, we get indeed n phi's downstairs, as needed in the definition of the Euclidean endpoint function. And perhaps to note that now, so in Minkowski space we had i's in here, because we had i's in here. For the same reason, we had e to the is, and this term was just another term in the real Minkowski action. But now in Euclidean space, we have e minus se, and we defined such that here we have a plus, so plus j phi, which means that there's no need to divide by any i's. And well, formally then we could also write, this is what we mean by z of j being the generating functional of these endpoint functions, that I could think of it as sum over n, 1 over n factorial, times the integral of products of these dxi's, and then g x1 xn is j x1 j xn. Right. So this is really what we mean when we say that this is the generating functional. As we said, this is the generalization of writing a generating function for some numbers a of n. Right? This would have been generating function. Now this generating functional means this statement. All right. So now let's move to understand perturbation theory. So perturbation theory means, as before, that our action must be written as a quadratic part and an interaction part. Tau denoted by Si. And we do this, we treat this exactly, this piece exactly, and this as a perturbation. Quadratic exact, and this is higher order and perturbation. So at a calculational level, we saw that one way to deal with it in the path integral was to use this saddle point approximation, right? So one possibility, I mean, this would be a non-perturbative possibility. Sorry, this would be a order by order, but simply of calculating the full partition function. And that would have been to expand this term into a classical piece, a quadratic piece, and then higher order, cubic, and so on. And for the leading part, we could use, for the leading part, which is the classical plus quadratic, we would use the saddle point approximation, that is Gaussian integration, and then the other ones would come as corrections. So that's a possibility. However, we also must keep in mind what is really something that we want to do. So we want to calculate, basically, we want to calculate transition amplitude. So we want some transition amplitudes where we have some particles coming in and some particles coming out, and then stuff happens in between that amounts to interactions, that in turn amounts to, that are described by this interacting piece. So in principle, these particles, since in quantum mechanics you can never measure things precisely, these particles have some wave functions, right? So particles with some wave functions. However, these wave functions amount to just some convolution with respect to the initial and final states with these wave functions. So the basic question that we will need to ask is, for states of given momentum, what happens? And then we can convolute with wave functions. But basically, what happens when we have particles of given momentum? They scatter, they do something, and then some other particles come also given momentum. However, as we saw, so in this case, the asymptotic states, the initial and final states, would correspond to states where we have a vacuum, and on top of the vacuum we have some particles with given momentum. Right? So that's somewhat different than what we did. However, as we will see, it's actually theoretically easier to calculate these Green's functions. And as we saw, we have a simple enough formalism, and today we'll do the rest of it. And then, in order to calculate these things that we're actually interested in, we will have to use some translation, some formula that relates the two. And this is, so, relation to correlation function, which are theoretically easier. Related by the so-called LSZ formalism. So I will just sketch a little bit what that means, because we will do things more precisely in steps a little bit later, after we'll define better these momentum scattering amplitudes. We'll have a first go at the LSZ formalism. But since the LSZ formalism actually involves also loops, which are part of quantum field theory too, in principle, this would be retaken in quantum field theory too. So, what we would need is the so-called S matrix, which is basically a product of some initial and final states with some interaction in between that we'll call the S matrix, or and so this S amounts basically to an interaction picture evolution operator between minus infinity and plus infinity. But so this is something that we want to calculate. But to relate to these Green's functions or correlation functions, one would need to obtain the residues of Green's functions at the external mass shells. That is to say, I put p squared external equal to minus minus m squared, or, well, like this. So the external momenta, all the external momenta squared are given to the minus m squared. And if I do this, so external of the residues of importantly, of course, this is all for external momenta, so this should be in for momentum space Green's function. Okay, and residue means that in principle this thing blows up. The Green's function, momentum space Green's function blows up when you put these things. But residue means that I have to divide by p squared plus m squared and then take the limit, right? That's what residue means. When you have a pole, you remove the pole. What you're left is called the residue, right? So I divide by these things, by these poles, and then the remainder, which is finite, is actually this S matrix. Okay? So let's say S Fi in some sense is limit when Pi external is minus Mi squared, this Gn P1 Pn over Pi squared plus Mi squared product. Right? That's basically the gist of this formula. And this is called the LSZ reduction formula. Okay, so there are details which I will not give now, but that's the rough idea. Okay. Oh, sorry. I said it wrong. So this is SFI is the residue, so that means I have to multiply. Sorry. Right. So Gn has poles. So this Gn is 1 over p squared plus m squared. So I have to multiply by these poles to obtain the residue. Okay. All right. Then that means that we have to understand a little bit what happens to the momentum space Green's function. So first of all, momentum space would mean that I would write the Fourier transform of the x-space guys, right? Dn x1, Dn xn into the I p1 x1 plus Dn xn, then Gn x1 xn, right? This would be the Fourier transform. However, I put the tilde in here because one has to note we have an obvious symmetry of space-time, which is translation invariance. Things have to be translation invariant, which means that Gn x1 xn must be equal to the one where I subtract an x0, so x1 minus x0, x1 minus x0. And then, for instance, I can choose x0 to be equal to x1, right? And then in this integration, I can change to xi prime equal to xi minus x0 for the other ones. So I would obtain that dn tilde is integral dn x1. So I keep this x1, which is equal to -0, separate. And then, so I will shift all of these x1s by x0, right? And then, so I would call this x prime. And then I'm left with just an x0 common, with x0 or x1 common factor. So ix1 for each of these integrations, p1 plus pn, right? And then this integral dn x1 prime, d2x, dn x2 prime, d, d, not whatever. I don't know why I call it n, d. X n prime, and then in here I would write x2 prime p2 plus xn prime pn gn at 0 x2 xn. Okay? So this is well defined.
Sorry,
as an independent number. Yeah.
Why are you calling these variables prime now? Where are you defining? Oh.
Yeah. So this is now the only dependence of x1, but you notice what this is. This is just 2 pi d delta d p1 plus until pn, right? And then this thing that is well defined, I will call Gn of P1 until Pn, right? I mean, strictly speaking, it's P2 until Pn, but because of this, because it's multiplied by delta, I can formally write it as P1. I can use the delta function to rewrite it in any way I want. So the point is that this, because of translational invariance, the naively defined, so just the Fourier transform, the endpoint function in momentum space, is a delta function for momenta times an independent Gn. And so what we will usually calculate will be actually this Gn, where we assume that the delta function is already done. All right. So just to remember, as I said, it will be much easier to work with these Gns. Theoretically, but we have to keep in the back of our mind that in the end, what we will do is translate through the LSE formalism to these S matrices that relate to physical scatterings. Okay, so all these things correspond to scattering in vacuum, so they come from the vacuum functional. These things correspond to scattering where there are some external particles of given momentum. Right. All right, so we were about to do perturbation theory, and the first thing that we'll do is define the so-called Dyson formula for this perturbation theory. And this is an interesting example of one of the reasons why I showed to you both formalism at the same time, both operator and path integral, even though this is not the traditional way people think. But I think this is simply because everybody has their own preference what they work with more, but as a theoretical physicist you have to know both cases. So, of course, the operator formalism came first. People first knew quantum mechanics in operator formalism, Feynman came later with his path integrals. So, as a result, for instance, this Dyson formula that I will describe for you here was first derived in operator formalism, and it looked kind of non-trivial in the sense people thought of this as some theorem. But we'll see it's almost trivial once we write it in perturbation theory. All right. So let's understand what kind of things we want to calculate. So, if we consider some free theory, then, and with a corresponding vacuum that I'll call 0, then I can consider some operator that depends on the fields of this free theory, and consider the vacuum expectation value of these operators. Right? And so I've calculated for you, I talked about how to calculate Green's functions, which are obtained by insertions of phi's into the path integral. So the Green's functions were 0 for, if we're in Minkowski space, I would have to put time ordering, right? But if I'm in Euclidean, time ordering kind of loses its meaning a little bit. But anyway, so we had this vacuum expectation value of some products of phi's, and that corresponded to a path integral of some phi's, right? But of course, now out of these phi's, I can construct operators. So first of all, I can take the limits where these x's are, let's say, at the same point, or instead of n points, maybe just 2 points, and then act with other things here, matrices, derivatives, and so on, that act with freely on both sides of the equation, both on this side and on the path integral side. Right? The result of all that is that I can basically replace this thing inserted in between vacuum states with any operator that depends on the phi's, right? Because by operator I mean something that, as a quantum mechanical operator, contains only the phi's, and then contain things like derivatives and matrices Mij, or if I have some index j of the fields, right? But all of these things are numbers as far as quantum mechanics goes, right? So they act on the same way here and the same way on the other side. So that means that, in general, I will obtain that this VEV is equal to the path integral, where I just insert this, but all phi, where phi is not anymore an operator, but just a number, a field, right? So all of phi. And then this is a free theory, so I weigh this with S0 of phi, right? Okay? But now, let me take the specific case. So consider the specific case where O of phi is just the interaction piece, right? In minus interaction piece that depends on phi. So let's say we looked at interaction of the type lambda phi fourth, right? That's some function of phi, lambda phi to the 4. And that's what we would get. So in this case, I would obtain that E minus interaction piece, depending on these phi's, is equal to that integral E minus S0 phi, E minus Si of phi. Right? And then moreover, I can now consider, consider besides this also another insertion of these phi's, original phi's in the Green functions. Right? So I can consider also phi of x1 until phi of xn. Right? So then I get that minus s phi of x1, phi of xn, e minus si phi 0 is integral d phi e minus s0 phi e minus si phi phi of x1 phi of xn. Okay. And again, these things are in Euclidean space, and as I said, normally I should have put here a time ordering product. But since we're in Euclidean space, time ordering doesn't make much sense. Time ordering is related to what we do when we do the Wick rotation to Minkowski space. So I didn't need to put that. Okay? So I can either consider this, or now by considering the generating functional of all these things, I can basically consider, instead of the products of phi's, just exponent with the sources, e to the j dot phi, right? Consider as 3 and write e minus si, and then e plus j dot phi, right? So finally, I can put this and say that this z of j in the so the z of j defined as the vacuum expectation value of e minus si of phi integral of x phi of x 0 is just that integral plus integral j of phi minus si of phi. Okay? So you see, now we relate this this particular amplitude with a path integral that we defined before as z of j, which is this path integral with e minus s0 and e minus si and integral j of phi, right? Just that now this is written as, note, this is the free vacuum, right? And with a free, so propagation with S0, in other words, using interaction picture if you want, right? The propagation, the quantum mechanics here is done with the free action, But inside this, I've introduced these two terms, right? So this is a particular type of perturbation theory. This is called the Dyson Formula. So as you see, this arose as a kind of almost trivial observation in path integrals. But the importance of this is very deep. In order to calculate this z of j, this thing, this path integral, I can use perturbation theory defined in this way, inserting these exponents e minus si and e to the integral j of phi inside the free action. Okay. So it's worth noting that this was defined initially since people were accustomed to this operator formulas, and moreover they did not think in this modern way of calculating Green's functions. They thought of calculating just S matrices, the things that you actually want to observe. So this was derived for S matrices in Minkowski space in operator formalism, and then it didn't look so natural as it does here. All right. To define perturbation theory, then the first thing we have to do is to calculate the free theory, right? So let's find the solution of the free theory. Right? That is to say, I want to calculate this path integral z0 of j that has only the quadratic piece, so this is integral d phi e minus s0 of phi plus j dot phi. And specifically, of course, this is integral d phi, if we're talking about this free scalar field. So exponent minus a half integral dx, and then let's write first d mu phi squared plus m squared phi squared. This would be the quadratic piece, and then plus this integral dx j of x 5x. But now I want to partially integrate in here to write this as phi operator phi. So z0j integral d phi exponent minus a half integral d dx phi, then minus d mu phi minus d mu plus m squared, like this, plus integral dx j of x over x. And of course, as before, I call this thing delta minus 1. Right? And moreover, we shift the integration by first writing so I have this linear term here. This is quadratic in fact, but then I have this linear term. So as before, I write this minus half phi minus delta dot j dot delta, whatever, delta minus 1 phi minus j dot delta. Then in here I get plus a half j dot delta dot j right? This is the thing that we did before as well. And then, of course, this whole pipe integral is Gaussian, but it's a number. So this gives just some number. It's independent of J anymore. This is called now phi prime if you want, or tilde. Then this thing, the integral phi tilde. Right? So this integral now is independent of J anymore. It's a number. And I'm left with this second term, right? And moreover, I can define this number as being, so if this was the vacuum to vacuum transition amplitude in the presence of the source, then this is at source equal to 0. Right? So the 0 of J is this 0, 0 times E 1/2. This thing means double integral J of x, delta x and y, J of y. And the propagator in here, we've said last time what it was. Well, we said in the case of quantum mechanics, but it's really the same thing now. So delta minus 1 was minus d mu plus m squared, so which means that I write this by Fourier transform. I Fourier transform, then minus d squared becomes p squared. And so this is dx e to the I p x minus y over p squared plus m squared, right? So this is the propagator, and like we noticed that last time, now p squared plus m squared is positive, so it has no singularities, no poles, right? And the poles only come when I rotate back to Minkowski space, when I Vic rotate back. So Vic rotate back to Minkowski. So by pi over 2. Then I get the poles, right? And as you remember, I said that the solution is to Vic rotate only by pi over 2 minus epsilon. So Vic rotate, I mean P0. And by doing so, we obtain the Feynman propagator. We said we have E0. And so we Vic rotate to do is pi over 2 minus epsilon to this, right? To this contour. And because there was no there were no poles in here, when I Vic rotate, that means closing this contour and writing the opposite one, minus contour for one of them, means that this contour is equal to this contour, right? And that only happens if I do the rotation with pi over 2 minus epsilon so that I don't touch these poles. Right? And in so doing, we obtain this contour, which was the Feynman contour. All right. So by doing this, we obtain that p e squared plus m squared becomes p m squared plus m squared minus I epsilon. But of course, this means p mu delta mu. This means p mu eta mu. That is to say minus p0 squared plus p vector squared. Right. So this is, let's say, p4 squared plus p vector squared. Alright, so by doing this rotation, it means that the propagated delta from there at S is equal to IT. This is Minkowski, this is Euclidean. And X is the propagator, the final propagator. Right? All right. So we've defined this Dyson formula, and we've seen that the solution of the free theory is as before. A constant times exponent j dot delta dot j over 2, where delta is this propagator that becomes the final propagator by rotation. So now to complete the perturbation theory, we have to write the equivalent of the big theorem. So before we had in operator formulas, I remind you, we had the Feynman theorem and the big theorem, and together the two gave us perturbation theory. And now we have the Dyson formula and the big theorem, which together will give us perturbation theory. And of course, together with the solution of the free theory as well. So the big theorem was somewhat difficult to see in the operating formulas. Not too difficult, but you know, it involved a certain amount of work. But as we'll see in path integral formulas, it's much easier to write, although it will be a bit more difficult to realize why this is the same big theorem as in the operator formulas, and we'll do this next time. But for the moment, let me just consider an example, and then the example is easily generalizable. So let's consider, for a function, let's consider a function of phi's, let's say. Let's take something like this. Phi of x1, phi cubed of x2, phi squared of x3. Just some product of phi's at different points. Okay? All right, so then by the same logic as used in Dyson's formula, I can write the VEV of this, the VEV in the free theory of this function, right? And then by the same logic, this is a path integral with e minus s0 of these things, phi of x1, phi cubed of x2, phi squared of x3. Okay. But now comes the trick. You remember how we obtain, for let's say, Green's function. So this would be like a particular example of Green's function, right? Where we also had some insertion of some phi's into a path integral. And the way we obtain them is by writing the path integral with an exponent e to the j dot phi, taking derivatives, and then putting j equal to 0. Right? So I would write this. I write this as, to obtain the phi, I just take dd j of x1. Then to obtain phi cube of x2, I take dd j of x2 cubed. Then dd j of x3, say squared. On this path integral d phi, e minus a0 plus j phi, and putting j equal to 0. Right? Okay? So this particular verb is given by taking derivatives on this thing. But this thing, you know, this is something that we've calculated before, so we'll be able to do it. But for the moment, for the next step, let me just note that there was nothing special about this function of phi's, right? I could have chosen anything and the result would be the same. This is just a convenient example so you can see what's happening. But then let me write in general. So if I have some finite j, so here at the end I put j equal to 0, but you know, that was just to obtain the case without j. But let me consider the case with j. And then, similarly, I would obtain, so here, you see, this is the same function f, where I replaced each field with derivatives, right? So I would write f of, and then instead of each phi, I would write ddj. Right? And then this acted on this thing, which is nothing but z0 of j. Right? Well, I defined it before, but it was basically this, right? Okay. Then, in particular, I want to use Dyson's formula. I want to find the equivalent of Dyson's formula, so I want to use this. So apply it for f being just integral g of phi, the e minus s interaction of phi, right? So in general, E minus S interaction, but let's say the part with a potential in the case of a scalar field. Right? So then I would obtain that Z of J, the path integral. So by putting this, I obtain Z of J as it here, is E minus integral ddx of V, just that now in V I replace phi with ddj. So let's say phi of V of ddj of x. And acting on z0 of j, And this Z0 of j was this thing, right? So n E1/2 j delta j. So most explicitly possible, d dx d of d dj of x acting on E1/2 integral d dx d dy d of x delta x y d of y. Okay? This is called the Wick theorem in path integral formalism. Now, this would seem like it's very powerful. It would seem like we've solved quantum field theory, right? As I said, all relevant formula can be obtained from Z of j, all the endpoint functions, from endpoint functions scattering matrices, and so on. And this is written as a given operator, differential operator, acting on some well-known function, well-given function. So delta is this, I replace here, everything is known, no? Well, so what's wrong with this? Can anybody tell me what's wrong with this formula? Why is it not a solution of quantum field theory? Well, you should have tried already when I wrote this. This is basically what this is, because I have there v of delta of j, which is something like phi cubed, phi fourth, and so on. This came from phi cubed, this from phi squared, and so on. So you should have tried foul when I wrote this already, because this is understood as a limit, right? The way I thought about it when I wrote phi cubed, I replaced phi cubed with ddj of x2 cubed, was to think of having independent j of x's and then putting them together at the same point, right? But of course, this is not well defined. In principle, I could get singularities and so on, right? When the points get together. So that's really what happens. So this thing is defined only formally, and really the only thing it means is thinking about perturbation theory, so expanding this in whatever lambda I have in here. So let's say this is lambda phi fourth, and I think of this as an expansion in lambda, right? And then defining at each order in lambda what I get from acting with this operator on this one, right? And then we'll see that even doing so, not surprisingly, since I expect when two derivatives come at the same point to get some sort of singularity, because, well, where does the derivative act on you know, it's if I have d phi of x1, d phi of x2 on some integral with phi of x, and then I put x1 going to x2, right? It's a bit ambiguous. When x1 is equal to x2, this, you know, how do I differentiate here and here, right? There's an ambiguity what that means. So the same thing will happen when I expand, and I will actually get infinities, and the way to deal with that would be renormalization. So this procedure, while it looks benevolent, it's actually not. It's just a formal expression that defines perturbation theory, but does not solve it. We still need to do much more. We need to regularize some infinities and renormalize them by absorbing them in parameters and so on. It's the whole theory behind it. All right. So next time I will show you explicitly how to calculate this in perturbation theory and show that indeed we get Feynman rules as before, and we'll see a little bit how to work with that. But that was everything that I wanted to tell you today. Do you have questions about this? Well, I guess we'll explain in more detail next time how perturbation theory works, but for the moment I hope we at least have some handle on a few things. Okay, so yeah, I guess that's probably enough. Let's stop here.